When most people imagine Germany, they picture high-end supercars racing effortlessly down open highways. But beyond the cars themselves, Germans take even greater pride in something else: their legendary highway network, where speed limits often feel like a suggestion rather than a rule. This system is known as the Autobahn. It's a road network so advanced that even engineers from the United States often ask the same question: how does Germany manage to operate one of the safest high-speed highway systems in the world? What looks like an ordinary stretch of road actually hides a completely different construction mindset beneath the surface. In Germany, a highway is treated as a fully engineered structure, not just a layer of asphalt poured over dirt. So how does the country use strict standards and cutting-edge construction methods to turn the Autobahn into the global benchmark for transportation engineering? Let's dive in and uncover what makes it so unique. Germany covers just 357,000 square kilometers, less than half the size of the US state of Texas. Despite that, it boasts a highway density nearly 7 times higher than the United States, with more than 8,000 miles of Autobahn stretching across the nation. Unlike many countries that simply pave a surface and label it a highway, Germany follows a completely different approach. Here, roads are engineered from the ground up. They are built, not merely paved. At the core of every German highway is a carefully designed 4-layer structure. It begins with a densely compacted subgrade, followed by a stabilized subbase, then a strong load-bearing base course, and finally a high-performance asphalt surface. This layered system is designed to resist cracking, deformation, and rutting, even when vehicles are traveling at speeds approaching 300 km per hour. But the real secret lies in the materials. Germany developed advanced polymer-modified asphalt mixes capable of handling extreme conditions. These surfaces can tolerate summer temperatures reaching up to 70 degrees Celsius, while remaining flexible enough in winter to withstand freeze-thaw cycles without cracking. These strict engineering rules are what make the Autobahn a place where high speed isn't just permitted, it's safely supported by world-class construction technology. Now let's start at the very beginning of the highway construction process, when the future Autobahn route is still nothing more than untouched forest. Before any machine ever arrives on site, engineering teams carry out an extensive preparation phase. This includes geological investigations, terrain and soil analysis, environmental assessments, and detailed construction planning. All of this data determines the exact path of the road, the required thickness of each structural layer, and the appropriate soil stabilization methods for every section. Only after everything is reviewed, approved, and verified are construction crews allowed to begin work on site. Once the site is officially handed over, the first task is complete land clearing. Trees, vegetation, topsoil, and natural obstacles are removed to expose the raw ground beneath. This step is critical because any remaining organic material could later cause settlement or weaken the road's foundation. With the area cleared, crews begin reshaping the terrain. High elevations are cut down, low sections are filled, and the entire route is molded to the designed profile. The goal is to create a continuous, smooth alignment with no sudden changes in elevation. To stabilize the ground, heavy vibratory rollers are then used to compact the soil. Depending on soil conditions and moisture content, operators typically make between 6 and 12 passes. Each vibration delivers an impact force of roughly 25 to 35 tons. The objective is to reach standard Proctor density, ensuring the ground is strong enough to support the massive loads generated by Europe's heavy freight trucks. Next, heavy dump trucks deliver crushed stone and deposit it in sections along the roadway. Immediately after, a motor grader spreads the material evenly across the surface, carefully shaping it to match the planned elevation profile. A water truck then applies a light mist, adding just enough moisture to improve bonding between the stones during compaction. A bulldozer follows to fine-tune the layer, ensuring both thickness and surface flatness meet strict engineering requirements. Once the shape is finalized, a large vibratory roller makes multiple passes, compressing the material into a dense and stable upper base. This crushed stone layer serves as the main load-bearing foundation, spreading vehicle loads into the underlying soil and significantly enhancing the long-term strength of the pavement. With the crushed stone base fully leveled and compacted, the roadway is ready for the concrete base layer. concrete mixer trucks begin arriving on site, each carrying precisely mixed concrete with controlled consistency. At the designated location, the mixing drums rotate to discharge fresh concrete into the receiving zone. By this stage, the prepared surface is already covered with white protective sheets. These sheets help prevent moisture loss and keep the base clean before concrete placement begins. An excavator uses its large bucket to lift each batch of concrete and feed it directly into the hopper of the slip-form paver. Because the loading process is continuous, the paver receives an uninterrupted supply of material, allowing construction to proceed smoothly without delays. The slip-form paver then distributes the concrete across the full width of the roadway using an internal auger system. Inside the machine, high-frequency vibrators compact the concrete, eliminate trapped air, and create a uniform density throughout the slab. At the rear, a forming mold shapes the concrete precisely to the required thickness and cross-section. This entire operation is controlled by a laser-guided system, ensuring exceptional smoothness and accurate slope. Operating continuously, the machine can construct dozens of meters of roadway within just a few hours. Steel dowel bars are stored in a loading tray above the paver, ready to be inserted into the fresh concrete as the machine moves forward. These dowel bars play a critical role by improving durability, reducing cracking, and transferring loads between neighboring concrete slabs. The paver's automated mechanism inserts each bar at the exact depth, spacing, and alignment specified in the design. This allows individual slabs to remain stable under traffic while functioning together as a single, continuous structure. Immediately after shaping, long finishing arms glide over the surface, smoothing and lightly compressing the top layer. This process removes surface waves and delivers the refined finish required for high-speed travel. It is essential for maintaining long-term ride comfort and reliable skid resistance. Once completed, the concrete base typically reaches a thickness of around 40 centimeters. As the surface begins to set, a specialized spraying vehicle applies a curing compound. This protective coating locks in moisture, slows evaporation, and helps prevent cracking as the concrete gains strength during the curing phase. This protective coating, typically made from paraffin-based or acrylic compounds, creates a thin sealing film over the surface. Its purpose is to slow down moisture evaporation inside the concrete, allowing it to develop maximum strength during curing. After roughly 30 to 60 minutes, once the concrete surface has hardened enough, specialized texturing machines move in. These machines use rapidly rotating brushes to lightly sweep the surface, forming fine longitudinal grooves. These grooves significantly improve tire grip, especially at high speeds. At the same time, the brushing process removes excess cement residue, leaving behind a clean, even finish before the next operation begins. The final step at this stage is joint cutting. Using precision cutting equipment, expansion joints are created at carefully calculated intervals. These joints control where cracking can occur and protect the overall pavement structure. Once joint cutting is complete, the concrete pavement is left to cure undisturbed for several days. Only after it reaches the required strength does the project move on to asphalt paving. Now comes one of the most critical phases in highway construction, laying the asphalt surface. In modern German and European projects, asphalt paving technology has evolved far beyond traditional methods. Dump trucks deliver hot asphalt, typically maintained at around 160 degrees Celsius, and unload it directly into the paver's hopper. From there, a system of conveyors and augers continuously feeds the material toward the rear of the machine, ensuring the asphalt is distributed evenly across the full width of the roadway. The key component is the screed at the back of the paver, a unit that vibrates, tamps, and presses the mix. While the asphalt is still extremely hot, the screed alone can achieve 85 to 92% of the required compaction. This allows the asphalt layer to be shaped, compacted, and smoothed in a single pass. The technique is particularly effective for thin surface layers such as stone mastic asphalt, which are typically only 2 to 3 centimeters thick and cool very quickly. Using conventional vibratory rollers on such thin layers can easily cause surface ripples or cracking. With modern automatic screeds, however, the finished surface remains smooth, uniform, and properly textured along the entire stretch of road. In the past, multiple types of rollers, vibratory, static, and pneumatic, were needed to reach the target density. Today, advanced pavers perform more than half of the compaction process internally. Pavers produced by the Vogel brand of the Wirtgen Group are especially well known for their accuracy, efficient material handling, and their ability to reduce roller usage by 70 to 80% compared to older techniques. After paving, a light steel roller may make a final pass for surface refinement, although many projects omit this step entirely because the asphalt already meets quality standards straight out of the machine. Thanks to these innovations, asphalt paving has become faster, more precise, and far more consistent, ensuring long-term highway performance. Once the asphalt has cooled and reached full stability, crews move on to the final stage, applying the road markings that guide traffic. Using laser alignment tools or guide strings, workers first mark the exact locations of lane lines, dividers, stop markings, and directional symbols before permanent striping begins. Once the layout has been finalized, a specialized road striping machine is brought onto the site. This machine applies thermoplastic reflective markings, which are heated to approximately 180 to 200 degrees Celsius to ensure strong adhesion to the asphalt surface. As it moves forward, the spray system produces lines with exact width and thickness according to highway regulations, while reflective glass beads are simultaneously applied to the hot paint. These microscopic beads reflect vehicle headlights at night, dramatically improving lane visibility and overall driving safety. Within just a few minutes, the markings cool, harden, and bond securely to the pavement, allowing the roadway surface to be fully completed and ready for traffic. The final construction phase before opening the highway involves installing the concrete safety barriers. These barriers are typically manufactured off-site in controlled factory environments. Each unit is cast in high-precision steel molds to guarantee consistent dimensions and accurate angles. During production, vibration tables compact the concrete, eliminating air pockets and producing a dense, smooth, and durable finish. After the concrete has fully cured, every barrier segment is removed from its mold, inspected for quality, and labeled according to its installation sequence. At the construction site, cranes or specialized lifting equipment position each segment exactly as specified in the design plans. Workers then connect the units using steel dowels or high-strength bonding materials, creating a continuous and stable barrier system. Using precast barriers significantly accelerates construction, minimizes traffic disruptions, and improves worker safety during installation and future maintenance. Once the barriers are in place, the engineering team performs a comprehensive final inspection of the highway. This includes checking surface smoothness, drainage efficiency, skid resistance, and the structural integrity of every section. Only after every component meets strict safety and technical standards is the highway approved for public use. Over time, however, even the best-built highways experience wear. After roughly 8 to 15 years of service, the asphalt surface begins to degrade due to weather exposure, heavy truck traffic, and repeated temperature fluctuations. At this point, the roadway enters the recycling phase to restore smoothness, traction, and structural performance. The first step is milling off the worn asphalt layer, typically removing between 2 and 10 centimeters, depending on the severity of damage. The milling machine grinds the old surface into small particles, transfers the material onto a conveyor belt, and loads it directly into waiting trucks. This process removes only the damaged surface layer while preserving the underlying base and structural layers. As a result, the road does not need to be rebuilt from the ground up, greatly reducing costs and shortening construction timelines. The milled material, known as reclaimed asphalt pavement, or RAP, is then transported to a recycling facility for further processing. At the recycling facility, the reclaimed material passes through a screening system that separates it by particle size and removes contaminants such as soil, oversized aggregates, and metal fragments. The usable asphalt is then grouped into consistent, uniform batches. This step is critical because reclaimed asphalt can show varying degrees of aging after years of exposure to traffic and weather. Accurate sorting and screening allow engineers to control quality and ensure the recycled asphalt performs at the same level as freshly produced material. Once the reclaimed asphalt has been properly classified, it is blended with new asphalt binder, fresh aggregates, and a rejuvenating additive. This additive restores flexibility to the aged binder, which has hardened over time due to oxidation. Inside the mixing plant, the reclaimed asphalt is carefully heated in stages to prevent overheating or burning. It is then combined with hot binder and aggregates following a precisely calculated mix design. Many modern asphalt plants are now capable of using between 30 and 60% reclaimed material while still producing pavement that matches the performance of brand new asphalt. This process is especially important because it conserves natural resources, reduces carbon emissions, and significantly lowers overall construction costs. Before the recycled asphalt is placed, the existing roadway surface must be thoroughly cleaned to remove dust, dirt, and loose debris, ensuring a strong bond between layers. In today's advanced resurfacing operations, a single machine can perform both tasks simultaneously. As the machine moves forward, spray nozzles at the front apply a thin bonding layer, known as a tack coat, directly onto the old pavement using asphalt emulsion or liquid asphalt. This bonding layer acts like adhesive, allowing the recycled mix to firmly attach to the existing surface and preventing slippage or separation under heavy traffic loads. Immediately behind the spray system, the same machine places the recycled asphalt mix onto the tack-coated surface without any delay. The paver spreads the hot material to the specified thickness, while the screed vibrates and precompacts it continuously, forming a smooth, uniform layer with proper initial density in a single pass. After placement, a combination of vibratory and static rollers further compacts the asphalt to reach the required density, reducing the risk of future rutting or cracking. Once compaction is complete and surface smoothness is verified, the roadway can be reopened to traffic, performing just like a brand new highway. You've now followed the full journey of how a modern German highway is built, maintained, and eventually recycled using advanced engineering and construction technology. All the information presented in this video has been gathered from multiple reliable sources. If you notice anything that seems incorrect or have additional questions, feel free to leave a comment below. Thanks for watching, and I'll see you in the next video.